So Thevenin's theorem states that any part of a circuit can be replaced by one voltage source and a series resistance. So any part, let's say we are talking about this part of the circuit, we want to replace this whole part. So Thevenin's theorem states that it can be replaced with a voltage source and a series resistance. Similarly, we can replace, let's say, this part with a voltage source and a series resistance. That's what Thevenin's theorem states. Now, how do we find the voltage source and the series resistance? In order to do that, let's say in this example circuit, we want to replace this circled part at this terminal. We want to replace it by a voltage source and a series resistance as Thevenin's theorem states. So what we do, we open this circuit here. So basically what has to be done here is this part will be R5 and R6 are taken away, so this remains as an open circuit here. This one open circuit. Once we do that, because we want to replace this part, we have disconnected the circuit at this point, and we will find the open circuit voltage here. Let's say this one, VOC, and that will be the Thevenin's voltage. So the whole circuit, this part can be replaced by a voltage source and a series resistance, and then this open circuit voltage will be the, which is also called Thevenin's voltage, will be the voltage source. And in order to find the resistance, once we find the voltage source, we need to find the resistance. So that can be found this by finding the equivalent resistance here. The resistance, what is found by looking at from here. Now there are voltage sources here, so what to do about the sources there? So we will make these sources inactive. When we say inactive, these are voltage sources, so they will be short circuited, and if they were current sources, that would be open circuited. So in this case, this will be short circuited, so this part will be just a short here, and this part will be just a short here, no voltage source. And then we will find an equivalent resistance if we look from here, from this across this terminal. Basically we are looking resistance here. So what we can see here is these two resistance are coming in series and then in parallel. So R1 plus R2 are in series and then parallel with R3. That's what we are getting. And then this whole part is series R4 plus R7. So R1 R2 in series, then parallel with R3 we get one resistance, and that one in series with R4 and R7 gives me that resistance which is seen from here. So that will be R Thevenin. So the whole circuit is replaced by one voltage source and one series resistance. This is this whole part. Now what we had here, we had two resistances which we were interested in. So that were R5 and R6, which we removed actually. So those two will be now connected here just like this, and we will have our circuit R5 R6. So if we want to find the voltage here, we can just find now. This circuit is much simpler than the original circuit. So this is what Thevenin's theorem says, and it is often very useful to solve a circuit when we apply Thevenin's theorem, especially when we are dealing with current in one branch or voltage across one terminal.